All right, so let me share my screen. All right, so hope everyone can hear me clearly and can see my screen. All right, fine. Okay, so today we're going to be looking at linear regression. And as I said, we will be introducing some of these algorithms to us. So this is mostly a conceptual and theoretical class. We are not going to be doing any coding yet, right? So I just want to get us to understand this concept very clear before we move into the implementation. So by next week, we're going to start the implementation, right? But the flow of the class is going to be from linear regression, then we're going to look at logistic regression. So the essence of that is to give you a foundation and understanding of what ML algorithms are, right? So once you get to understand this linear and logistic regression, it's going to give you a basis to understand the other ones we're going to be looking at, right? So once we've done those two, we'll move on to how to implement this ML and how to build our models using sklearn. So by next Saturday, we're going to look at the logistic regression, and then on Sunday, we're going to look at how to implement linear regression and logistic regression fully in sklearn. All right, so by next upper week, we're going to look at some other machine learning algorithms and then look at some other concepts in machine learning and some other algorithms as well. So if we are unable to cover everything, then we're going to look at fixing a class outside of our normal class time, where we cover some of the topics that we need to cover. All right, so for today's class, we'll start up with linear regression. So I believe I sent a material like before this class. I think that should be on Friday on linear regression, right? I actually sent a material on machine learning actually, right? I don't think I sent for linear regression. So that should cover the basic aspect of machine learning. The recording for yesterday's class is already available, right? So if you've been able to go over it, that's fine. If not, then I think you should do that after this class, so as to get a better grounding of what we explained and discussed yesterday. So linear regression, now, this might be looking or sounding new to some of us, right? For those of us that have been exposed to ML before now, or those of us that have actually like taken courses, statistical courses, we'll probably have heard of linear regression. If not linear regression, you probably have heard of regression itself. All right, so I'm going to be explaining what these things mean, breaking it down for us to have an understanding. All right, so linear regression, first of all, it's an algorithm, basically. It's a machine learning algorithm, and we're going to look at what this algorithm is used for. All right. So as you can see on the screen, linear regression is one of the easiest and most popular machine learning algorithm. That's basically where we are starting with it. All right, it's one of the easiest actually and the most popular ML algorithm. It's the statistical method used for predictive analysis, basically. So what we are going to be using linear regression for is to create a predictive model All right. Let's say you want to be able to predict something in the future. What you're going to be using, you can use some of these algorithms like linear regression to do that predictive analysis. All right. So generally, we have different kind of analysis. We have descriptive analysis, right, which we've looked at already, where we are just like analyzing past the data to know or to gain insight from it. So that is where data analysis comes in. So we also have this predictive analysis as well. So yeah, give me a minute, give me a second, please. Let me attend to something. Right, so linear regression, as I said, it's for predictive analysis, and we have several kinds of analysis. We have descriptive, we have predictive, we have prescriptive, right? So we have, but that is not the point. That is not what we're discussing today. So I just want to let us know that we have predictive analysis. So predictive analysis is when you really want to use your data to make predictions for the future, right? And one way to achieve that, or the most common way to achieve that, is using machine learning. All right. So linear regression is one of the techniques that you can use for predictive analysis. Okay. So remember, I think when we were discussing data science at the beginning, I talked about how to use like I talked about data science and data analysis and the differences. And I think I talked about data science being descriptive, while data analysis has a prescriptive aspect to it, right? So that's basically what I'm talking about now, right? So linear regression is used to make predictions, basically. Okay, so predictions, the predictions that are going to be making is going to be depending on the kind of data that they are working with, right? So the linear regression algorithm is used to make predictions, basically, for continuous or numerical variables. All right. So I'm going to just have to explain some things so you get to understand what I'm trying to say here. So when we talk about continuous or numerical variables, we are talking about variables, obviously, that are numbers, right? So in a data set, or when you want to create a machine learning model, you normally have two kinds of data, all right? You have what we call the dependent variable, and we have what we call the independent variable. I think I'll just have to create a distance, so I'll be illustrating it as we explain. So we have what we call the dependent variable and the independent variable. So these two kinds of variables can take on different names. You can call the dependent variable the y variable, and you can also call the independent variable the x variable, right? We can also call the independent variable the features, and we can call the dependent variable the target. I'm basically giving you an understanding of the kind of data, or I'm basically giving you notations for of the data that will be used when training your machine learning, right? Because when you get to hear all of this, you shouldn't be confused. So let me just write them out so you can just see them. I'll explain. So we have types of variables in ML, or let me just say variable notations in ML. So we have variable notations in ML. We have dependent, independent. We have independent. It can also be called X variable. Let me just say right variable there. It can also be called X variable, and it can also be called features. All right. So we have dependent variable, which is called Y variable, and which is called your target or labels. All right. So these are the things you need to know when it comes to your data set for machine learning. You have to know which of your variable is your independent variable and which of your variable is your dependent variable. And the type of the data type of your variable or your variable type will determine the kind of algorithm that would be used. All right. So in linear regression here, we saw that linear regression is used to make predictions for continuous or numerical variables. So this continuous or numerical variables is referring to the dependent variable here. All right. So the dependent variable for the dependent variable data type would have to be a numerical or continuous variable for us to consider using linear regression for it. So let's assume this dependent variable is a categorical variable. You would not be able to use linear regression for that kind of data set. All right, you're going to have to use a different algorithm. All right. So this is something you need to note. The kind of dependent variable will determine the type of algorithm that will be used. I remember in the last class we talked about two types of ML tasks. Talked about types of ML tasks. Can someone just fully remind us of this of the types? Right, I think we looked at it yesterday, and I mentioned them. So can someone just tell us the types of ML tags that we have? All right, thank you. So we have classification task. Remember that ML task is different from ML type of machine learning. We have types of machine learning and we have types of machine learning tasks. All right, so those are two different things. So when we talk of types of machine learning, we're talking about supervised, unsupervised, and reinforcement. But when we talk about ML task, we are talking about classification and regression task. All right. We have classification task and regression task. So these are the two types of ML task. And each of these ML tasks has the algorithms, the ML algorithms that are used to perform those tasks. So classification tasks I think we looked at yesterday. An example of ML algorithm that we have for classification task is what? Can someone just help us with that? We looked at it yesterday. So can someone just mention one type of classification task algorithm? Yeah, thank you, Hamza. We have SVM, support vector machine. All right. So any other one? Yeah, we have decision trees. decision trees. Yeah, we have naive Bayes, we have logistic regression. All right, so let's just stop here. So basically we have these different algorithms, and they can be used for classification tasks. So I'm going to explain what we mean by classification tasks. But for regression tasks, we have linear regression. Can anyone help us with other algorithms for regression tasks? We have linear regression. We have decision tree as well. Decision tree can also be used for it. So let's just keep it here for now. Let's just keep it simple, right? So basically, for classification tasks, when we talk about classification tasks, we are talking about tasks that has the dependent variable to be categorical variables. So for classification tasks, our dependent variable would have to be categories, all right, for us to consider using categorical machine learning models or machine learning algorithms, basically. So classification tasks, categories, let's just put categorical, let's just say categorical targets or labels. For regression task, we're going to say numerical targets or labels, all right? So these are the two types of ML tasks. And this is the relationship between the data type and the ML task, and also the ML algorithm. So you need to understand this relationship, right? So for you to select a particular algorithm, you have to understand the tasks that you're performing. And to know the tasks you're performing, you have to look at the data set. And in that data set, you have to look at the categorical variable. Sorry, you have to look at the dependent variable, which is your target or your label. All right. So I'm just going to use some the data set we've used before as an example. So let me see. See if I can just create something here. All right, so let's see if we can import a data set. So I'll show you. All right, so we have something like, let's just assume this is the data set we're going to be using for our ML model. Let's just assume, all right? So we are going to be looking at I'm just going to bring out a particular variable and label it the target variable. So in this case, let's say what we want to do, we want to predict the price of each product using all the other variables, okay? So we're going to bring out this price variable and now consider it our target variable. So, and the ML task we want to perform is to create a model that can predict the price of a product using these other variables that we have that are called independent variable. So in this case, what kind of ML task am I going to be using for this problem, this ML problem? What task am I going to use to solve this problem? Exactly. So I'm going to be using a regression. This is basically a regression problem, a regression task. I think that's the best way to put it. This is the regression task, all right? And knowing that it's a regression task, you then have to like look at those specific algorithms that can be used for regression tasks. So that's how you actually think about ML problem or ML task. You first look at your data set and understand the kind of data set you are given and know what particular variable you are trying to predict, okay? So let's just assume it's a price variable. You know that this is a numerical variable. Then you automatically know that this is a regression task. And then given it being a regression task, will now determine the kind of ML algorithm you use. So in this case, you can actually use a linear regression algorithm, all right, which is very good for performing regression tasks. So let's just switch it and assume that we want to predict the product categories, right, for this particular data set. I'm just using this data set to just illustrate. Don't really think too much about it because it might not really make sense. So, but let's just assume this particular variable is what we are trying to predict. So this variable will be called what now? This product category variable, what will it be called? No, you are not. I don't think you are getting the question. I'm saying this category, this variable that we are trying to predict now, what will it be called, or what is going to be the notation or the name for this this variable? Okay, I'm seeing some people saying independent, dependent, targets, and all of that. X. So I'm going to have to explain the whole thing again. But basically, this is called our dependent variable. Do you know why it's called dependent variable? Because it is dependent on other variables for its prediction. You want to predict these particular categories. For you to make that prediction, you have to rely on other variables to make the prediction, all right? So there are other factors that you have to consider before making the prediction of this particular variable. So that's why it is called your dependent. It depends on other variable for its prediction, right? So the other variables that you're using to predict that variable, they are called the independent variable. So you can have one independent variable or you can have multiple independent variables, and that will actually determine the kind of linear regression task you'll be performing, all right? So that's basically just how you can approach selecting an ML algorithm via your data set or the problem that you're trying to solve, all right? So dependent variable, they are usually the variables that you are trying to predict. And for you to make a prediction, you have to rely on other data to make that prediction. You don't just make a prediction out of nowhere, okay? So let's just assume you want to predict the match score of a particular match. Let's just say Man U, Tottenham is playing they're playing their finals next week, and you want to predict the score, the match score. So the match score in that case is what? The dependent variable, okay? And the match score will depend on several factors, like the previous matches that have been played between the two clubs, the club current form, the club status, and a whole lot of other things, all right? So those other factors, those other data that you are going to be considering, they are what we call the independent variables. They are what influences the prediction of the dependent variable, okay? So the match score that you are trying to predict is dependent on other factors, on other variables. Remember why told us about variables. Variables are values that can take on different data. So they vary basically. So you know that your dependent variable always depend on other variables or other factors, which are called independent variable. So your dependent variable is also called what? It's also called, before I say, I just want us to have an interaction. I think it kind of facilitates understanding. Your dependent variable is called what? Someone said target, features, Y, label, feature, target, Y, target. All right. If you said target, you are correct. If you said features, you're not correct. If you said Y, you are correct. If you said label, you are correct. So your dependent variable can also be called your target variable. Target variable basically means that is the variable we are trying to predict. That is the target variable. That is the target variable, the variable we are trying to predict. If you also mention Y, yes, Y variable is the, it can be another name for our dependent variable, all right? So for our independent variables, that basically meaning those variables that will help you in predicting your dependent variable or your target. They are called independent variables, or they are called your X variables, or they are called features. So I need you to understand this thing. It's actually very important. So these are notations and terminologies that you need to know before you start doing ML, anything ML, right? So you have to know how these different variables interact with each other and their notation as well. All right, so let's just proceed because we need to finish up with this today. So linear regression algorithm shows a linear relationship between a dependent Y and one or more independent variables, hence called linear regression. So this linear regression algorithm, what it's trying to do is it's trying to understand the relationship. It tries to map a relationship between your dependent variable and your independent variable. Okay, so when you have, let's say the sales data, the retail transaction data that we just showed you now, what our linear, if you use our linear regression model for it, what it's going to do is that it's going to like try to understand how this let's just use price. It's going to try to understand how price relates with other variables. So it's going to map a relationship between these two types of variables, right? So that is basically the process of training. So during training, what you are trying to do, you are trying to show or trying to like tell the try to map a relationship basically, or trying to create a model, right? A model is like a representation of something. You're trying to like represent that relationship, trying to create a relationship and just basically map a relationship between your dependent variable and your independent variable. So once your model can understand the relationship, then it can use that understanding to predict future variables. All right, can use to predict like future values, right? So that's basically what linear regression is for. That's basically what all algorithms does, right? So all the machine learning algorithms, they try to map or create a relationship between your dependent variable and your independent variable. The only difference is that these different algorithms, they take a different approach in doing that. All right. So those approaches are what we are going to be explaining in our classes, in our this class and subsequent classes. All right. So they take different approaches. Remember what we call them algorithms, because an algorithm is a step-by-step process of solving a particular problem. That is the base meaning of an algorithm. So we can have several approaches to solving the same problem. So the reason why we have multiple ML algorithms, because we need these are just basically different approaches to solve the same problem. So linear regression can solve the same problem as random forest. All right. You can also solve the same problem as, let's say, SVM for regression tags, basically. The only difference is just that these different algorithms, they have their strengths and weaknesses. So depending on the task you're doing, you can select a particular algorithm, and that algorithm will perform well than another algorithm, right? So there are a lot of things you have to you have to take note of when choosing an ML algorithm. All right, so that's just basically it. The linear regression algorithm tries to map a relationship, and this relationship is always a linear relationship. Although we'll get there, we'll get to the assumptions of linear regression, basically. All right, so you understand why we call it linear. Okay, we understand why we call it linear. So the linear regression algorithm is used to map a linear relationship. So for linear regression, the relationship has to be linear. The relationship between the dependent variable and the independent variable has to be linear. When we say something is linear, what do we mean? Can someone help us? When we say something is linear, what do we mean? Yeah, thank you very much. So when we say something is linear, we basically mean that the relationship or the direction of their relationship is in a straight line. Okay? So when you map or represent the relationship in a visual, you are going to see that the direction of their relationship will be in a straight line. It might not necessarily be a perfect straight line, but you can see a progression in a straight direction. So that's actually a very, very important assumption for linear regression. Before you use a linear regression, you need to be sure that the relationship between your dependent variable and your independent variable is linear. But that's not what we are talking about now. We are going to look at, if you scroll down, you see at the end, we are going to see what we call assumptions of linear regression. And these are the things that these are the criteria that has to be met before you select linear regression. So you can see the first assumption is linear relationship, okay? So we are going to look at this later, but I just wanted to bring it up here so you understand why we have linear relationship here. All right. So linear regression algorithm shows a linear relationship between a dependent variable y and one or more independent variables x, right? So that's basically what linear regression is for. So since linear regression shows a linear relationship, which means it finds how the value of the dependent variable is changing according to the value of the independent variable. So it's the same thing they were saying. We are trying to understand how the independent variable influences the dependent variable. So for you to have a very good model, you need to see a lot of those relationships, right? You need to see a lot of them. So that is why when you are creating a machine learning model, you use a lot of data, right? Because the algorithm or the model has to see a lot of examples, so you understand the pattern. It understands the pattern and tries to create a more robust model that can give you accurate information or accurate predictions. All right. So if you use just like 5 data points, like 1, 2, 3, 4, 5, and you want to use it to create a model that will predict something, you are going to get your predictions are not going to be very accurate, right? Because the model is just seeing 5 data points, which is not robust enough. Like it needs to see enough examples for it to be able to establish the relationship. All right. So you need a lot of examples before you can establish what a relationship. So that's basically what happens in linear regression. So let's just move on. So we have the formula for linear regression. So this is the mathematical aspect of it. So if you're familiar with a line, the equation of a straight line graph, this is the equation here. We have y equals to beta naught plus beta 1 and xi. So all these things are basically just the representation of the different variables in our data. So if you've done the equation of a line on a line on a straight graph, you'll be familiar with what we are seeing here. Y is equals to mx plus c. Basically, it's been a while, right? So it's basically the same pattern here. So this our y here is what we are trying to predict. This is the dependent variable. All right. So this I you are seeing here is just each example. Like if you have 200 rows or 200 observations, each of them is going to take on this I, right? So it's going to be performing this equation on each of those examples, all right? So, but basically, this Y here, it corresponds to our label, our target variable, or our dependent variable. That is what we are trying to predict. So every other thing on the right-hand side, they are the equation or the operation that would have to be performed to get these predictions. So this beta that we have here is just a constant, right? It's our intercept basically. So just keep that aside for now. This is what we are going to be focusing on majorly. So this beta one is what we call slope or coefficient. So when we actually train a model, what we are trying to learn, we are actually trying to learn some parameters. All right. So I know some of these things would be new to us and to be sounding somehow, but just take it as you're saying it. All right. You will definitely get to understand it better. So what we are trying to do when we train an ML model is that we are trying to learn parameters that is going to give us the best performance or the best predictions. All right. So this beta one here is a parameter that we're going to be learning, and the parameter is called your slope or coefficient here. So this is something that is being learned. It is learned during the process of training. Okay, it is learned during the process of training. It is not something that it gets from your data set. So the only values that are gotten from your data set are Y variable and your X variable. So this X variable is what your independent variable. Okay. This is your independent variable. Remember when I talked about like tuning to a radio station in yesterday's class, and you get to a frequency that is not very clear, and then you start like trying to turn the knob of that your radio so as to get a very clear frequency. This is basically the same thing that machine learning algorithm does, right? Or your training process does. During your training process, your algorithm, the model is trying to tune this value here. This value that you're seeing here is trying to tune it to a point where the accuracy is going to be better. So at the start of your training, we are going to have a random number here. Let's just say 0, to start from 0. So from that 0, it will start to change the values, start to change the value. So you don't have any issue. You don't have anything to worry about this thing here. The algorithm is what is going to actually determine the best value that you have here, right? So during your training, this particular value would be tuned. Basically, it would be tuned to a particular point where the equation here, everything here is going to give us a very good performance, a very good accuracy. All right. So I'm not going to go into depth on the inner working of this, right? But if you want to read it or if you want to look it up, the whole process is what we call back propagation, all right, or gradient descent. So it's a lot of step-by-step mathematical process that involve that is where you're going to see your algebra coming in, and all of those mathematical equation. I think let's not even go there for now. But this equation here is the simple linear regression equation. Let me just recap. This is your Y variable, what you're trying to predict. All right. This is your X variable, the independent variable. So in this case, this is a simple linear regression where you just have one single independent variable. All right. So this is just your this is just a single independent variable. In cases where you have multiple independent variables, which you always have for most parts of your work, you are going to have this kind of equation here. You're going to have this kind of equation. Let me zoom in. This kind of equation you're going to have Y equals to your intercept, or your constant intercept, and then you're going to have a coefficient or slope for each variable. So let's assume you have 10 independent variables. You're going to have beta 1 times x1, which is your first variable. You're going to have beta 2 plus times x2, which is your second variable. Still, you have your last variable here, beta 10 times your last variable. So all your variables will be paired by a coefficient, basically. So the training process will determine how much weight or value will be assigned to each of your variables to give you a very good prediction. So the way you determine a good prediction is by you first get your, you just randomize, right? Give your coefficient random values at the start of the training, which your algorithm will do on its own. You don't have to do anything, but it initializes it randomly. And after the initialization, everything will be calculated and you're going to get a Y value. So the way your model would know if this Y value is accurate is that it's now going to compare this predicted value with the original label. All right, let's say at the let's take this price. Let's go to price. Let's say this is what we want to predict here. We want to predict 76.15, and then at the first iteration, it's going to take in all these variables like product ID, quantity, remove transaction date. It does not do any. It's not necessary unless you want to like change it to months or days of the week. So you have cash, you have closing. So you have all these variables here as your independent variables. So once you slot all these variables into the equation randomly, and your model randomly assigns an initial weight to your coefficient, it's going to give you an initial prediction. So that initial prediction can be something like, let's say, it can be lower than this value, or it can be higher than this value, but the target or the original value is 76, and you want to ensure that that prediction is very close to 76, all right? So let's say the initial prediction was 700 and something. You can see that if you compare it with this 76, it's actually far off from it. So what your model will do is that it will try to tune all the coefficients of this independent variable so that it is going to become close. The value is going to come close to 76.15. It probably would not be exactly 76.15, but it should be close enough to 76. It might be able to bring it down to, let's say, 80 something, or it can bring it down to, let's say, 70 something. All right, so it's close enough. So when you like do this, you do it for each observation. So this is what we call the learn. This is what happens during the learning process, the training process, basically. So this is what our ML algorithm or our model is trying to learn. It's trying to learn the coefficients that will give us the best, or that will try to minimize the error between the original or the true label and the predicted label, right? So that's what it's trying to do. It's trying to minimize the error. The error is the difference between the predicted and the original. Let's assume the predicted value. Let's say the predicted value is, let's say, 300, and the let's say the true value is 76.15. So what linear regression will try to do is that it will try to minimize the error between these two values. So this is the predicted value from your equation, and this is the original, the true value. So this is for the first row. So it tries to minimize this error. It tries to bring this 300 to the point where the error will be minimal. Let's say we're going to have something like 82, or let's say 70, or let's say 72. So it tries to do that to a point where the error is minimal. So if you check the error in this case, let's just use a very simple error formula. Let's subtract this true value from this one. So the error in this case would be 76 minus 72, which is going to be 4. So the error is 4. So this error now is very minimal. The initial error we have here was 300. If you subtract 76 plus 300, you're going to see that you're going to have a very high error, 200 and, I don't know, let's say 30 something or 20 something, 24. So you can see that it has minimized the error from 224 to just 4. So that's why we usually have what we call iterations during our during training. So iteration is basically doing something over and over again. It goes for the first round, it gets a predicted value, right? right? Let's say 300. It compares it with this true value. It calculates the error and checks it and sees that it is high. Then it goes again to the next iteration, calculates the before it calculates it, it tries to modify all the coefficient of all the independent variable by changing it, by tuning it like a radio, tuning it, so that we'll get a predicted value that is closer to this true value. So let's say the second iteration, we get something like let's say 230 something. You can see that the error has reduced. So this is second iteration. So it goes over and over and over again till it gets somewhat close to this true value, till the error is minimized. That is the aim of machine learning. That is the aim of training in machine learning, trying to minimize our error as much as possible. All right. So I'm trying my best to break this thing down so you understand, because it can actually be quite elusive initially, but I believe with time you're going to grasp this concept and understand it. But this same concept is something I'm going to be saying over and over again as we keep looking at new algorithms. All right. So, but this is for linear regression. This is the formula for linear regression, and I think I'll just have to tell you that this is a simple linear regression because it has just one independent variable. All right. So just one independent variable, and this is gotten from your data set. All right. This is your y variable, and this is your x variable. So these other values here, they are lengths during training. So let's just move on. We are going to look at types of variables in linear regression. I think I've explained this already. So linear regression hinges on the relationship between two key types of variable. We have the dependent variable, which is also called the target variable. Before I continue, hope we are all still following at this point. I need feedback. Hope we are all still following. Okay, on a scale of 1 to 10, how much are you understanding what we've discussed so far? On a scale of 1 to 10. Okay, I think that is okay. That is encouraging. All right, so let's move on to what we have. So we have what we call the dependent variable, as I've explained, which is also called the target variable. So this is the variable you are trying to predict or explain. All right, this is the variable you are trying to predict or explain. It's the outcome you are interested in, and it's often continuous in linear regression. You can see where we looked at the target variable type, which will determine the algorithm you're using. So we are looking at linear regression today. So the outcome variable, now you can see another name has come out. Now you can also call it outcome variable. So the target variable is often continuous or numeric in linear regression, right? So it can be numerical or like continuous variable, basically. So this is an example. Now imagine you're analyzing the relationship between studying hours X and exam scores Y. The exam score Y is the dependent variable, right? So let's just assume you want to understand the relationship between exam score and the number of hours put into study by students. So in these two cases, the exam score is what you are trying to predict, okay? So that exam score will be your dependent variable. It is depending on a variable called study hours, which is what your independent variable. And this ML problem or this task basically is a simple task because of it has only one independent variable, which is your studying hour, all right? So this is a very, very simple example for linear regression. So the exam score is a dependent variable because it's the value you are trying to predict based on the number of hours studied. All right, so you're going to have a lot of the data, like let's say 200 to 500 data points, and you pass it into your ML and it tries to understand the relationship between study hour and the exam score. So after you map the relation, most likely see that the higher the study hour, number of study hours, the higher the exam score. All right, so that is the relationship. So if you want to predict a particular exam score and you have a certain study hour, you can see that your model will be able to, at least to a very good accuracy, predict the exam score for you. All right. So we can also say that in linear regression, the dependent variable is linear. So I'm still repeating the same thing. So that is just it for the dependent variable. So we have the independent variable. So the independent variable is also called the predictor variable. All right. I think I didn't say this one. So you can use it like this. You can use dependent. You can pair it in this way: dependent variable and independent variable, target variable and predictor variable, X variable and Y variable. So these are the three pairs that you can use. So if you are using dependent variable, you have to, just for easier understanding, you have to go with independent variable for your for the other ones. If you are looking at target variable, you should go with predictor variable. If you are going with Y variable, you should go with X variable, like for the two variables, right? I think if you're also going for labels, you should go with features for your X, all right? Labels and features. Thank you, Bello, Janet. If you are going for input, you should also use output, right? So output variables for your X, for your Y, input for your X. So there are a lot of like notation for these variable types, all right? So I just need you to understand it and not confuse or allow yourself get confused, okay? So for your independent variable, this is the variable you believe influences the dependent variable, right? So this variable basically influences the dependent variable. It is often used to make predictions about the dependent variable. I think I've explained all this already. It can be plotted on the horizontal axis of the graph, and we'll come to that later on. So in our example that we used before, studying hours X is our independent variable. It is the factor you think affects exam score. All right. So before you select variables that you can use to predict, you have to be sure that this variable has an influence over your target variable. For instance, now this this data set we have here, before you use your data set for machine learning, you don't just use everything. You assess each of the variables to be sure that they have meaning, basically, like they can actually influence your target variable. So in this case, customer ID really doesn't, normally you should know that the ID doesn't have any influence basically on the price. So regardless of your customer ID, it won't actually affect the price. So you can just drop this customer ID. Transaction date as well, like as it is now, it probably won't have any influence, or unless you want to segment the dates into, like, say, morning, afternoon, night, or Tuesday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or the months of the year. So unless you have it in that format, then fine. But if you have it in this raw format, it probably won't have any effect on price. So you have to also do all these things to analyze your feature. And although we are going to look at that later on, it's called feature engineering, right? But this is basically how you go about your variable. So where were we? Okay, so that's how we go about understanding the variables that affect your dependent variable. You don't just use any variable that you want, that you feel like you want to use. You have to assess them. That's why domain knowledge is usually good when it comes to things like this. If you're working with health data and you want to like create a model that can predict something, you need to have an understanding of each of those variables and know whether this particular variable can affect the thing you are trying to predict. All right. So if you need to do research on it, definitely go on and do the research. Just make sure you have an understanding on the relationship between those two variables. Let's push on. So we have two types of independent variables. We have single independent variable, or what we call simple linear regression. So we are looking at linear regression today. So when you have just one independent variable, you are going to be using simple linear regression for that task. But when you have multiple independent variables, you're going to be using what we call multiple linear regression. All right. So in this simple linear regression, you're just having one independent variable, like just study hour, all right? Just study hour and your target variable. But if you have like more variables, like let's say you have studied hour, you have difficulty of the exam, you have student prior knowledge, and these are multiple variables. So you're going to be using multiple linear regression for this particular task. And I've shown you the formula for them. This formula is for simple linear regression. It has just one variable and one coefficient. And for the multiple linear regression, we have, where is that one? Where is that? Okay, see it here. We have, this is the formula for it. So it uses different formulas. So we have this for that, and we have this for simple linear regression. All right. So we are going to still look at that. So that's basically it for the types of independent variables. Right, so just keep that at the back of your mind. So there are some things to note. Like I'm just going to just say this one so as you have it at the back of your mind. Linear regression assumes a linear relationship. I'm repeating this again, and I'm still going to repeat it. It assumes a linear relationship between the independent and the dependent variables. All right. So it assumes. So before you run your training or perform your training, you need to ensure that there's a linear relationship between your independent and your dependent variable. And what this means is that the change in the dependent variable is expected to be consistent with the change in the independent variable. And that is basically what linear relationship means. As I have explained it, a straight relationship. It can be positive, it can be negative. Remember when I talked about correlation, I talked about positive correlation and what negative correlation. So it's basically the same thing as that. So we also have here another thing to note is that logistic regression is the other kind of algorithm, ML algorithm that you use for categorical variable. So let's if our target variables in this case is a categorical variable, then you can't use linear regression. You use what we call logistic regression. We're going to actually look at logistic regression in the next class, but we don't use linear regression for it. We use logistic regression. So you have to know the type of target variable you have so as to determine the algorithm you're going to be using. So if your target variable is categorical, let's say pass or fail, let's just assume you want to predict if a student will pass or fail the exam using study hour. So instead of exam score, you are now having pass and fail as the target variable. You would not use linear regression again. You would use logistic regression and some other regression that are suited for classification tasks. So this is the classification task because of the type of dependent variable we have, right? So in such cases, you use a different machine learning technique like logistic regression, which is designed for predicting categorical outcomes. So by understanding these variable types and their role, you can effectively set up and interpret linear regression models for continuous prediction tasks. All right. So you can read up all of the other ones that we have there. So now let's quickly discuss what we call regression line. But before I continue, hope everyone is still following. And what on a scale of 1 to 10, how much are you assimilating what we've explained so far? All right, fine. Okay, so let's move on. So we've looked at linear regression. We've understand or we've explained what linear mean. So let's explain what regression itself mean. So regression line actually is what linear regression uses in predicting or making prediction. All right. So regression line is what linear regression uses in predicting or making predictions. All right. While regression is a way in statistics or machine learning to find the relationship between variables, basically. So regression is just a technique, it's a statistical technique basically that you use to understand the relationship between dependent and independent variable. So the line is what represents that relationship. So the line is the regression line. It represents the relationship between these two variables. And regression line is always a straight line. Regression line is always a straight line. All right. Although there are adaptations to linear regression, right? When you can't really use a straight line relationship, you can add some polynomials to kind of make your line a little bit curved. That's when you now start having something like polynomial regression and all of that. But we're not looking at that. We're just going to focus on linear regression. So linear regression is used to map relationship between a linear relationship, very important, between a dependent variable and an independent variable, right? So a regression line can show two types of relationships, a positive linear relationship and a negative linear relationship. I think we all understand this one already. I think we've looked at it before when we looked at scatter plots. So if the dependent variable increases on the y-axis and the independent variable decreases, then such relationship is termed as positive linear relationship. So when one is increasing and one is also increasing, it's positive linear relationship. For example, it's obvious that the higher the number of hours studied, it's more likely that you're going to have a higher exam score. Although that particular variable is not sufficient enough to get you to make that prediction, right? So that is why multiple linear regression is always what you use most of the time, because a single variable is not good enough to make a good prediction. So, but let's just use that. So the higher the number of hours studied, most likely you're going to have a higher exam score. So that is a positive linear relationship. All right. So for a negative linear relationship, we're going to have where in this case the dependent variable decreases while the independent variable increases. So it's like an inverse relationship basically. So this is a diagram to illustrate what we are saying. So this is your y-axis and this is your x-axis. So your regression line is always a straight line. So this one here we have here is a negative linear relationship. So as the y is decreasing, the x is increasing. As you can see, y is coming from up, that which means is decreasing, while x coming from left to right, which means is increasing. So in this case, we're having your y to be increasing. You can see it's coming from down to top, and also your x is also increasing as well as it's coming from left to right. So this is a positive linear relationship, and this is a negative linear relationship. All right. So when working with linear regression, our main goal is to find the best line. All right. So now I need you to pay attention to this. Whenever I tell you that I need you to pay attention to this, or I repeat something multiple times, just know that thing is very important to note. The goal of linear regression is to find the best line, the best fit line, basically. Let me the best. So the best fit line, that means the error between predicted values and actual values should be minimized. So this is why I explained the other time, right? So the goal is to find the best fit line that minimizes the error between the predicted values and the actual values. So all those things I explained before, all this mathematical stuff, they are now represented in a graph here, all right? So you are looking for the best line that is going to minimize the error between the predicted value and the actual value. So in this diagram you're seeing here, the predicted value are the values on this line here. So this line is basically representing the predicted value. While the dots that are scattered all over, they are the actual values here. So to calculate the error, you literally, what linear regression does is that it calculates the distance between each point to the predicted line, right? It calculates the distance between this one, basically subtracting this for this as I did before, and it does it for all the data points we have here. You can see how much of computation that is. So let's say if you have 100,000 data points, it will calculate the distance. It will create a line. It will create an initial line, right? A random line. And what determines this line is what? The coefficient. That is the slope and the intercept. That be theta and our b1 for our x variable. So the point at which this line touches the y-axis is our intercept. So it gives a random intercept as first. Sometimes the intercept starts from 0. So it just gives a random intercept and a random slope, and then it will use those numbers to generate a line, right? Let's say the line is coming from here like this. And then when it creates that line, it now calculates the distance between the predicted the values, which is the line that we just created, and the actual values, which are all these data points. It calculates that mean error and then gets a value. All right. So it now uses that value to kind of change this. It now starts changing the slope value, that is the coefficient value, and the intercept value to give us a smaller error value, right? Basically. So the line will be changing as we are changing the intercept and the slope until we have a very good line that minimizes the error. So in gradient descent, there's what we call local minima. So when it gets to that point, that is the point at which we can attain the lowest error possible. So it stops the learning process at that point, and then we have our model. So this is going to be our model, and this is the model you would use in interpreting any future value. So if you extend this line like this, you can use it to predict as many values as you can. So let's say you want to predict the happiness score of people that have income of, let's say this is times 10,000. If you have this is $6,000, right? So here will be $7,000, here will be $8,000. If you extend this, you have $9,000, $10,000, $100,000, $90,000, $100,000, and so on and so forth. So if you want to predict the happiness score of those with $100,000, you are going to just trace the value here on the x-axis to this line as it is extending. So it's actually going to extend infinitely. So you can use it to predict as much value as you can. So if you trace the 100,000 up here where it meets the line, that point where it meets the line, you will now draw it, trace it to the y variable, and then this is the predicted y value. So let's say for those that are making $100,000, your happiness score will be somewhere around this place. Let's say 7 or 8 or something like that. So this is basically how linear regression works, right? So the graph would actually give you a better understanding. So we looked at the mathematical aspect, and I believe you should be able to have a little intuition or understanding of how linear regression works, right? So that is it for regression line. So the regression line is the line that you use for making predictions, basically. So that is what linear regression is trying to learn. It's trying to learn the best. It's trying to get the best regression line that best fits your data. So the best fit is the one that has the minimum error, right? When you calculate it, the error between the prediction and the actual values. All right, so let's just proceed. So this is an explanation. This is your dependent variable here. This is your independent variable. These are your data points, and this is your line of regression. All right. So that is basically the illustration or an explanation of your regression, your linear regression. So let me just ask a very simple question. For this particular line that we have here, what is going to be the intercept? For this particular line that we have here, what do you think will be the intercept? That's actually very good. So we actually understand. So from here, if you draw this line and extend it, the point at which it touches the the y-axis is what? 0. So the intercept will be 0. All right. So in this place, you are going to have, in this formula here, we are going to have 0 here. That is the value that we are going to have here. And then the slope in this place is going to be, we're going to have to calculate the slope. Remember, we calculate slope is going to be, we're going to draw something like a triangle from this place to this place, and then calculate y2 minus y1, x2 minus x1, all of those things that you learned in secondary school, right? So you calculate the slope, and it will give you a value, right? Thank you, Nigeria. Change in y over change in x. So you calculate the slope, and that slope value is going to be what you're going to have in this place here. So these two values are changing. And when I mean changing, I mean when you change this line, if you tilt this line a little bit, whether up or down, the intercept and the slope value will change. So the intercept and the slope value are the values that are used to represent this line. So if you have an intercept value and a slope value, you can use it to draw any line that you have here. All right. So those are the two values that are being learned during training in linear regression. All right. So the point of linear regression is to get that intercept value and the slope value that will give you the minimum error. All right. The best error possible. So that is just it for linear regression. I hope we're all still understanding so far. There's a website that kind of illustrates this very well. So I'm trying, just give me some seconds. Let me see if I can get it. Just give me a second, because this is actually going to drive all this explanation home. And that is the aim of this class. I really want us to understand the concept. The implementation of linear regression is actually very straightforward, but the theoretical aspect is the most important. So you need to understand what you're doing so as to perfectly implement. So the implementation is really easy. It's just the theoretical aspect that is very, very, very important and sometimes can be difficult to grasp. So just give me a minute. Let me see if I can get the website. I wish I can get this, because this would actually drive home this point. Let me see if this is it. No, this isn't it. Okay. I think I've got it. I've gotten it. All right. So let's see. All right. So this is just going to give you an understanding of how a regression line is created, or how your intercept and slope value affects a regression line. So this is not the exact website I was looking for, but I think this one will just do. So now there are different components to this graph. So now we have I think we're still going to look at the R square, which is the metric to use to determine the performance of your model. But this is what we call a regression line here, right? So this line is like, let me see if I can move this. All right. So you can see that as I'm moving this line here, I'm not really getting the intercept and the. I just want to see if. Anyways, but basically, as I'm moving this line, you can see that the R square here. So I'm going to come to R square. R square is a metric that we use for regression. It basically gives us an assessment of how the model is performing. So the R square value is usually from 0 to 1. So the higher the value, the better your model. All right, the better your regression model. So in this case, it is 76, right? But if I bring it down here a little, you can see it's increasing, 79, because the error is being minimized. All right, if I bring it down here, you can see it's getting better as the intercept and the slope is changing. So the slope is just it's just how okay, you can see that the R square here is increasing. You can see that. So basically, this line just tells you everything that you need to know. So let's see if we can get. Let's see where the best line is. So 92, 93, 94. That's the problem. I can't get the slope. And this is not the website I was looking for, right? The one I used for demo previously usually give us the intercept and the slope. But I'll look for that and send it to the group. So class rep and assistant, please remind me of that. So this is just an illustration of how your intercept and slope influences your regression line. So you can see that as I'm moving this line here, my intercept and slope, they're actually changing. All right. And that is what the ML algorithm is trying to learn. All right. So it's trying to learn the values that would give me the best regression line. All right. So that's basically it. Yeah, thank you, Kodri. We're actually still going to get to those metrics, ASCO and all of that. I'm going to explain it. So, but this is just an illustration. So let me just go back. I think I'll get the other one and then send it to us so we can like look at it. So that is it for regression line. Now let's go to the types of regression we have. We have simple linear regression and multiple linear regression. We've actually looked at these things already. So simple linear regression, it has just one independent variable and one dependent variable. All right, so the model estimates the slope and the intercept of the line of best fit, right, which represent the relationship between the variables. So the slope represents the change in the dependent variable for each unit. So this is just change in y over what? Change in x. That is the definition of your slope, basically. While the intercept represents the predicted value of the dependent variable when the independent variable is 0, right? So that is the intercept, right? So the intercept is usually, the definition of the intercept is the value of your predicted variable when your independent variable is 0. So when you set all your independent variables to be 0, that is a multiple linear regression. The value of your intercept, the value of your dependent variable, that's your prediction, is actually your intercept. All right, so that is basically what the intercept represents. So that is the formula for your simple linear regression, and this is the formula for your multiple linear regression. We have it here. So I've explained all of this already. But because of time, let's just go straight to what we have next. So we're going to look at the evaluation metrics for assessing our linear regression models. All right, so we're going to look at these different metrics. All right, so we have several of them. We have the mean square. All right, we have the root mean square error, we have the mean absolute error, we have the R squared, and we have the adjusted R squared. All right, so these are the different metrics we're going to be using to explain how well our linear regression model is performing. So this can also be like translated to all other regression models. So any other model you're using for regression task, you can as well use the same metrics, right? So you can use the same evaluation metrics to evaluate any regression model that you have, okay? So it kind of translates to all other regression models, not just linear regression. So I'm just going to explain these metrics quickly. We have your mean squared error. So your mean squared error, basically, it measures the average squared difference between the actual Y values and the predicted Y values from your model. All right. So it measures the average squared difference. So this is the key thing here. So what this means is that for each of, if you have 200 data points, you would, when you've gotten your regression line, what linear regression does is that it calculates the difference between each data point and each actual value and the corresponding predicted value. So it gets each value for those 100 data points, all right? And then it kind of adds all those differences. They are called errors, right? It adds up the errors and then get the mean and then get the it gets the square of each of those errors first before adding it, and then gets the mean. As simple as that, right? So it's going to be something like, let's say the error for your first data point is, let's say, 70. So you're going to be having something like 70 squared. All right. You will now come and go to the next. You will now go to the next data point. Let's say the next data point error is minus 50. You are not going to get it's not going to be minus 50 squared. So you have 70 squared plus minus 50 squared plus this squared. So you calculate the error for each data point. If you have 200 observations or 200 data points, you are going to calculate each individual errors. You square each of them, get their the value, and then get the mean of those of the errors, of the squared errors, right? So that's going to be your mean squared error. So this is one of the popular metrics that is being used. So a lower MSE indicates a better fit, as the errors are smaller on average. All right. So we are going to see this in practice when we start like actually using it data and creating our linear regression model. So you're going to see how it calculates the error for you, and you can use the error to see how well your model is performing. All right. So mean squared error is calculated by squaring the errors and then averaging them across all data points. This is just what I just explained now. All right. While easy to interpret, squaring the errors can give more weight to larger errors, potentially overemphasizing their impact. So you can see we have different errors here. So some of the errors are useful in some certain case, while some of the errors would not really give you the best overlook on your model performance. So you have to understand when and where to use each error. So I'm just going to go over all of them and point out the pros and cons. All right, so we have root mean squared error. So root mean squared error, it takes the mean of the mean squared error. All right, so it takes the mean squared error and converts it back to the same unit as your dependent variable. So this allows for easier interpretation of the error magnitude in the original scale. So in this mean squared error, you can actually fall into this kind of problem where bigger errors would actually impact the final value. So where you have larger errors, in this case, might be probably like maybe an outlier or something, affects the overall error, right? So mean squared error is not robust to outlier. I would just put it that way. So while mean square error has this con, root mean square error is like the solution to that, right? So root mean square error provides a good average error your model makes in predicting Y. So this allows for easier interpretation of the error magnitude. So it actually takes away magnitude of errors in your data, right? Basically meaning that it is robust to, let's say, bigger value. So there are some errors that might be very big. So if you add up those errors with the other ones, it probably affect the general error. So you need to kind of let's just use the word neutralize it. So to neutralize it or to remove that effect, you can use root mean squared error metric. All right. So these are the two metrics that we can use. So we also have mean absolute error. So mean absolute error calculates the average absolute difference between the actual Y values and the predicted Y values. Right. So it doesn't square your errors, right? So it just calculates the average absolute difference. So if you have minus something, you get the absolute value for that error. So when we say getting an absolute value, it basically mean removing the sign. If it's a negative sign, you remove it and you just retain the value. If your error was minus 50, you remove that. You have to take away the minus and retain the 50. So that is what it means. So it kind of gets the absolute difference between your actual Y and predicted Y and then average it, right? So it doesn't square, it doesn't do all of those things. It gives equal weight to all errors regardless of their magnitude, all right? So imagine you have, let's say, an error of, let's say, 500 and something, and you square that error. You are basically escalating that error. That is what happens when you use mean square error. That is why it kind of give more weight to larger error, because you are squaring each error. So if you have that larger error, it escalates it by squaring it, right? So root mean square error basically just brings it back, like reducing the impact of those magnitude, and then gives you an easier interpretation. Why mean absolute error doesn't square at all? It just gives you the absolute difference as it is, all right? So we also have R squared. So R squared is actually a different metric, all right? So R squared, why this mean squared error, root mean squared error, and mean absolute error, they are used in your training, like to kind of get the best fit. R squared is quite different. What R squared does is that it represents the proportion of variance, or let's just even put it this way. It shows how much of the variation, like it tells you how well your regression model fits the data by telling you how many percentage, all right? It tells you like, let's say 90% of changes in exam score can be explained by the study hour variable, right? So I told you that the regression, the R square is between 0 and 1. That is from 0%. You can convert this from 0% to 100%, right? So let's say your regression, your R square value is, let's say, 70 or 0.7. So the explanation is that only 90% of the changes in the target variable, which is your exam score, can be explained by your independent variable, which is your study hour rather. Right, so that's actually a very strong relationship. You most likely don't get a 100% R squared value. Right? It most likely won't happen. So, but most of the time, if you get from 80 to 90, it's actually a very good R squared. It shows you the predictive power of your variables. All right, so it shows you the predictive power of your variable. So if you want to know how well a variable is predicting a particular target variable, you can use your R squared value to know that. So if your R squared is 0.2, that's very bad. It tells you that only 20% of the exam score changes, rather. Like, let's just use that. So the variation in a particular variable, only 20% of that variation can be explained by your independent variable. Like, I can understand that there's some there I'm introducing some kind of terminologies here for those that are new to this, like you might not get it immediately, right? But just trust me, you are going to get to understand everything as we move forward. So these are just the different. Okay, we also have another one here. We have adjusted R squared. So our adjusted R square is almost the same thing as R square, right? The only difference is that the adjusted R square is used to it take note of additional independent variables, right? So when you add new variables to your model, like it actually take notes of those new variables, right? And then adjust for that, right? So it now tells you okay, as you see here, a higher adjusted R square compared to R square suggests that the additional independent variables likely improved the model's fit without overfitting. So it's just taking into consideration a new independent variable that you are including. So if your R square value for a particular variable is 70, and then you add a new variable, the R square for that variable can actually drop or increase, right? Sorry, the adjusted R square might drop or increase depending on how much impact the new variable you are adding have on the predictor variable, on the target variable. So there's actually a lot of things going on here. When it comes to model evaluation, you have to pay attention to all of these things, right? And we're going to be unraveling them as we proceed with the class. And when we start like with implementation, that is when you're going to actually appreciate it better, because you see all these things in action. And this is actually just for regression tasks, right? These metrics I just explained now. Classification task has its own different set of metrics that you also need to understand as well. So evaluating your model is a very essential aspect of machine learning process. If you don't, if you can't evaluate your model, you won't get a very good model, and there'll be no point even training a model if you can't have something that can accurately or to a good extent make a prediction, right? So you want to make sure that the prediction your model will be making is quite accurate to a certain extent, all right? So that is the reason why we are like bringing in these different evaluation metrics. But these things will be taking our library is actually going to be like abstracting all of these evaluation metrics, and we'll just have to be using the functions to calculate all of them. So we don't have to do anything, like literally we don't have to do anything, just to calculate it using a particular method, get the value, look at the value and see if it's good enough, and just monitor it, go back to our training, add some things, do some things to make sure that we can get even a better performance from our model and all of that. So the whole process is an iterative process, basically, right? You do this, you check if what you've done is good enough. If it's not good enough, you go back, you look at what you can do to make it better. You do that. It might be removing a certain variable or adding new variables, or like just tweaking some things, like some hyperparameters, which we are still going to look at, and then getting the evaluation metrics again, looking at it and seeing if it's actually getting better. And to some extent, you can just decide that, oh, this is good enough, and then you can stop there and then like save your model or deploy your model depending on how you want to use it. All right. So these different metrics, we're going to still be looking at them moving forward. So I believe by next class we look at logistic regression, and then go into SKLN, where we'll start like working with real data and actually building our model and evaluating them. So most of these things I've said in this class would make more sense by that class, by then. All right. So that is going to be it for that. So let's look at when to choose the right metric. So as I said, you don't just blindly choose a metric. So your metric will often depend on the specific context and goals. So there are 3 things that you need to consider: the error magnitude, outliers, and model complexity. All right. So in error magnitude, you should use RMSC for interpretable error values in the original scale. So if you want like your error to make more sense to you, you should use RMSC, because if you use something like MSC, you're going to be getting large, high error values, which it will be more difficult to explain, right? So RMSC will actually keep your error within the confines of interpretability, so you can actually see your error and kind of interpret whether it is very high or very low, right? So for outliers, it will be encouraged or advised to use MAE. So if you're as I explained the other time, if your data has outliers, MAE would kind of keep them in is kind of robust. Our RMSC actually is also kind of robust to outliers as well. So, but MSC is easily affected by outliers, right? It's actually easily affected by outliers. So it's not advised to use MSC when you know your data has outliers. All right. So also model complexity. So it's advised that you use adjusted R-square to compare models with different numbers of independent variables. So as I said, your adjusted R-square puts into consideration additional variables that you have in your data. So if you want to like use it to know how much impact an added variable would have, you'd use your adjusted R-square to check that. So you can have several models, and then maybe one model has an additional variable, another one has, so you can just use the adjusted R-square to just make that comparison. So don't worry, there are a lot of things to unravel going forward. Machine learning is very, very theoretical. There are a lot of things you need to know. The easiest aspect of machine learning is actually just like using the libraries and the tools. Understanding is the main thing. Like having an understanding of what you are doing is very important, like very, very important. So there are a lot of assumptions that you need to take note of. There are a lot of things that you need to consider before choosing what to use in building your model. All right. So let's move on to the last thing for today, which is the assumptions of linear regression. So I think I mentioned this initially, where I mentioned linear relationship. So linear regression relies on certain underlying assumptions to produce reliable results. So you don't just choose linear regression as your go-to model because you know that you can solve regression tasks, right? You actually have to ensure that it meets some certain assumptions. All right. So first assumption is going to be linear relationship. As I said, linear relationship is a very, very essential assumption, because the inner working of linear regression will require a linear relationship between your dependent and your independent variable. If not, the results you'll be getting will not be very reliable. All right. So it doesn't mean it won't work. It would work most times, but the outcome or the output will not be a very reliable output. All right. So that's just one of those assumptions. So you can see here we have three regression lines, or three charts here. The first one, this is a simple linear relationship, right? Just one variable on the y-axis and one variable on the x-axis. So if you plot it on a graph, you can use it to assess the relationship. So the relationship between this is actually linear, because if you draw a straight line, you can use it to like know if the relationship is linear or not. Right? There are also other statistical methods that you can use to assess a linear relationship, right? But for the sake of this class, we're just going to look at this. So we have this. It can be positively related or negatively related, whatever direction, but it should just be a straight line. So this relationship now is non-linear. You can see that it's actually not a straight line. There's a curve to it, right? So a linear regression won't be suited for this kind of data set. Right? Once you plot your data set and it has this kind of relationship, you most likely shouldn't use linear regression. You should look for another algorithm to use. All right. So that is it for the first assumption. So the second assumption is independence of errors. So now we have what we call errors or residuals. So the the errors that we calculated initially, most times they're called residuals, all right, but they're also called errors as well. But let's just call them residuals. So I need you to get familiar with some of this terminology. So residuals are basically, technically they're not the same thing, but let's just, for the sake of simplicity, residuals are basically the difference in the actual and the predicted value. So the same thing I said as errors before is what we are calling residuals now. So if you get all the residuals basically, all right, you've gotten the difference between the actual and the predicted value, and then you plot the residuals. The residuals should be independent of each other. All right, there should be no correlation, there should be no pattern signifying that this residual depends on the previous one or the one following all of that. So on this graph here, you can see this residual here. After we get the residual of all the data points and we plot it and we get something like this, this basically tells us that there's no relationship, right? Everything, all the independent residuals, all the individual residuals are independent, right? So this is the assumption, another assumption that needs to be met. But if we plot that, we see something like this, not necessarily just this, we see a pattern. This is going to tell us that we don't, linear regression would be the best algorithm for this particular data set because the residuals are kind of dependent on each other. All right, so this is another assumption that needs to be met. All right, so what this means is that the errors or residuals are assumed to be independent on each other, meaning that the error for one data point doesn't influence the error for another data point, all right, as we have in this graph here. So the next one that we're going to look at, the next assumption is what we call homoscedasticity. All right, so that is actually a mouthful, and I really don't like saying it, right? But this basically means is looking at how constant the variance is. All right, so homoscedasticity is like another assumption that basically looks at the variance of the errors. So we are still looking at the errors as well. So if you actually plot the variance of our error, so we will look at something like this. If we have this kind of spread, this spread basically shows us that the variance is constant. So the variance here, the variance is just the like should I say the difference and all of the difference between this point and this point here is the same as the difference between this point and this point and difference between this point and this point. So the variance is constant. That's what we call homoscedasticity. All right. Why this other one is not following that assumption? You can see that the difference between this point and this point is not the same as the difference between this point and this point, and it's not the same as the difference between this point and this point. So this is what we call heteroscedasticity. So your data set, the errors basically have to be constant. The variance of the errors have to be constant, right, to meet one of the assumption of linear regression, which is homoscedasticity. And if it doesn't, then you are going to have to look at another algorithm, all right? So this, we've looked at three of them: linear relationship, independence of errors, homoscedasticity, and then we're going to look at normality of errors. So all these things are focused on error. So normality of error is when you get your error values and you use an histogram to check the distribution of our errors. So our errors have to be normally distributed, having a bell-shaped curve. So if you look at it and it's normally distributed, then fine, it meets this assumption of normality of error. But if it doesn't, then it does not meet the assumption, right? So that is basically another assumption that needs to be made. So the errors or residuals are assumed to be normally distributed, right, around the mean zero. So you should already know what normal distribution means by now. And we also have two other ones here, right? So this one are just extra. So we have no multicollinearity. So this is where the independent variables are not highly correlated with each other. So another assumption, this one is actually quite important, right? So if you have two independent variables and you check the correlation between these two variables and they are highly correlated, you do normally that you remove one of those variables defects on your. It's just basically having your dataset. So you should not have multi-collinearity where you have two independent variables highly correlated with each other. Okay. So if X variables are strongly correlated, it can lead to difficulties in isolating the individual effects of each variable on Y. But this is really not a very sometimes you most likely don't pay attention to this particular assumption, all right? So the last one we have here is autocorrelation. So I think this is almost the same thing with this that we have here, independence of error. I think you're just saying basically the same thing. So these are the different errors these different assumptions of linear regression. So before I use linear regression, these assumptions have to be met. The truth is that most times people don't really check these assumptions. Just go ahead and use linear regression and check if it is giving us a very good performance, right? If it's not giving us a good performance, that is when these assumptions will now be checked. We'll now start checking if there's a linear relationship, if there's an independence of errors, if there's homoscedasticity, if there is normality of error, and all this multi-collinearity and all of that. So if your linear regression is not giving you a very good performance, it's most likely that some of these assumptions have not been met. So what is mostly done is that the linear regression algorithm will be used to create your model first, assuming that all these assumptions have been met. And then if it's giving you a problem, then you start checking the assumption. But most times, the ideal thing to do is to check this assumption first. But you just try to be very practical and realistic with things, right? So most times it will give you a good performance, and you don't actually need to check the assumptions and all of that. So, but this is the ideal thing to do, is to check for this assumption first before proceeding with selecting your the linear regression algorithm for your task. All right. So that's it for today. We've looked at quite a lot. So, and let me just end with this. It's important to remember that these are assumptions and real world data may not perfectly adhere to them. However, checking for these assumptions and addressing any violation can help improve the reliability and interpretability of your linear regression model, right? So there are techniques that are available to handle some of these violations, like data transformation or using alternative algorithms for non-linear relationships, right? So the one that is mostly checked is linear relationship, this assumption, right? This is one of the most important here. Right, so I believe this has given you an idea of linear regression. So this is a very important algorithm that is used in machine learning for regression tasks. All right. So we are going to wrap it up here. I believe I've done my best to explain this, and it's fine if you don't get it immediately. Right, it's fine. This is a very new concept. This can be a new concept to most of. This is most likely a new concept to most of us here. So I'll just give you a time to go over it and go over the recording and go over the material. There's nothing we're implementing today, just the conceptual level. Please, I'm going to send some video materials to help you understand it better and drive some of these points home, and for you to also see some fresh perspectives as well to linear regression. So that's going to be it for today's class. If you have any question, please let me know, and then we call it a day. Any question? Okay. All right. So in the absence of no question, I'm going to be ending the class. So if possibly question comes up along the way, don't fail to ask in a group and tag me as well. And yeah, please do well to. This one is very important too. Okay. Is anybody saying anything? Nigeria, are you saying anything?
was thinking of a question. I don't have a question at the moment. All I wanted to say is thank you so much, sir, for breaking these things down the way you do. Thank you so much. I appreciate it.
All right, thank you. It's my pleasure. All right, any other
Yes, sir, I
things?
have a question.
Okay, go ahead, please.
Thank you for your lecture today. Like, it's something I've been anticipating, but I just want to get clarity. The independent and dependent variable, is it also the same as future metrics and target vector?
Yeah, it's the same thing. Future metrics. This is basically when you convert your independent numbers, right? Because before you train your model, you have to like do a lot of pre-processing and feature engineering. So we're going to get there. This is just an introduction. We are going to break your feature numerical representation. Feature matrix is like a numerical representation of all your independent variables, while your target vector is a representation of your dependent variable. This is what we call it feature matrix. Matrix is basically taking into account multiple variables, while a vector is a single variable. That is why your target vector is called target vector, because it's just one variable. So it's a vector. A vector is like representing one. Remember in when we look at NumPy, a one-dimensional NumPy array is called a vector, while two-dimensional, three-dimensional, they are called matrices, right? So we are still going to even look at how NumPy is related to machine learning. Like everything we are going to be doing is still going to come back to NumPy, right? So feature matrix is simple as independent variable, but it's a numerical representation, while target vector is your target variable. I hope that clears it for you. All right, so let's take the next question. Janet, Bello, Janet, you asked a question. You're raising your hand, so please ask your question.
Good evening, sir. So my question is on now the evaluation metrics. I mean that area seems somehow actually, but then I know that we are going to like train the model and then come back to like testing. So should we say that during that evaluation metrics, you already know you've already know how the model will perform, and probably there might not be need for testing. I'm just saying because it is an evaluation metrics, like you've already get to know what the performance of the model will be. And then the other question will be, do we necessarily need to use all that metrics before we can ascertain that, okay, the model is good, or just pick one and go?
Okay. Yeah, that was a good question. So for your evaluation metrics, the thing is that machine learning process is an iterative process. So before you get your final model, you're actually going to what you're going to do is just trial and error, basically. So the trial and error is basically training and evaluation. You train, evaluate what you train and evaluate what you train. So this is just a general overview. When we look at the detailed implementation, then we are going to be introducing and looking at how we can test, we can create a test data set for testing and all of that. So, but when we get there, we're going to like break them all down. But you only know the performance of your model when you evaluate it. Right? There's no way you can know how well your model is performing until you evaluate it. It's when you evaluate it with your metrics that you know how well your model is performing. All right. So that's basically the importance of evaluation metrics. It lets you know how well your model is performing, whether it's performing very well, and if you need to stop at that point, or if you need to continue training it and trying to make it get better. All right, so that's basically what what is there, or what the evaluation metrics does. Please, yeah, I think you asked the second question. Can you just bring it up again? I think I missed that. It's
Yes,
just one question.
yeah, the other question is if we can just pick one or we have to like use the whole of
Okay.
that matrix.
Oh, you actually use one. Yeah, you use one. So you select one. If that one is, yeah, you select one evaluation metric, and depending on the nature of your data and nature of the work you're doing, you have to select the specific one as I've explained. If your data has an outlier, you know that you don't want to punish, you don't want to like punish bigger errors, so you use a metric that would not give more attention to those bigger errors. So you use something like mean average error for evaluating your model. You don't use mean squared error, right? So if you want to pay more attention to errors, then you probably just use MSC, all of that. So the thing is just that I need us to just understand it at this point, right? We are literally going to look at all these things in details more. It's just an introduction, right? So, but it's good that you ask these questions. We don't use everything at the same time. We don't use mean square or MSC, and it's just these are options, right, that you can select from. So you pick from one of them depending on you pick the one that is best suited, basically. All right. So, and your knowledge of all these things will determine which one you pick. So that is why it's essential to have a basic understanding, like a foundational understanding before you start training model. Like most places that you go to, you just say learn machine learning this in 2 weeks and all of that. What are you trying to do? They're just trying to like introduce you to sklearn, model.fit XY, this, that, and all of that. So you don't really know what's going on under the hood. And the thing is that I'm actually not even going very deep into this. We are just like giving you the foundations. If we're really going too deep, we are now going to have to look at gradient descent. We are going to look at back propagation, and we are going to look at how all of these the cost functions and all of those things that work in the back end to kind of give us our errors and tries to minimize the errors and all of that. But this is actually a very good place for you to start, and it's necessary that you start here so that it doesn't just overwhelm you and just it doesn't just overwhelm you, basically. All right. So I think that's going to be it. Then another question. We need to end now. It's already late. Another question. All right. Thank you very much, everyone, for your time. I just want to let you know that you are doing very well. If you've stuck with us to this point, it's not easy at all, right? Especially for machine learning, it's really not easy. For those that are even just like getting introduced to it, just stick around with us. It will get better. You would get to understand it like you understood Python, like you understood data analysis. It's not something that is reserved for some set of people. It's not something that is reserved for people that did mathematics in school or people that already had an experience with it at all. It's reserved for those that they are persistent enough and curious enough to actually learn, right? It's English I'm using to teach. I'm not using French to teach you machine learning. If I was using French to teach you, then you probably like just give up, right? But I'm using English, the same English I've been using to teach you all this while. So why won't you understand it? Why shouldn't you understand it? You will. Just take your time. It might take you some more time than the other ones that you learn, but you definitely get to understand it. So it's not a big deal. I'm just telling you. I was once at this point few years back. So yeah, just continue like doing what you're doing, continue learning, continue like keep on just keep your mind open, basically, and maintain your curiosity, and you'll get all the things that you want to get out of this. So thank you very much, and do have a splendid night, and enjoy the rest of your week. Please let me know the things you've learned in this class. I'm really curious to know. Please, I really want to see as many responses as possible to this. I don't just want to see 5 or 6. I don't just want to see is this particular person that is always posting long trying to like remember her name. What's her name again? I like seeing things like this. All right. Anyways, I think I'll remember it later. But please, I don't want just a set of people doing that. I want everybody here, like, pointing out. Okay, yeah, Juliet. Yeah, Juliet. Thank you very much, Juliet, for what I'm always seeing what you're doing. So keep it up. So I don't want Juliet and Nigeria and some other persons doing that. Let every other person do that as well. It will help you and help every one of us. So thank you very much, and good night. See you next week, Saturday, by God's grace.